What is up, guys? Today we have another LeetCode video. I have a lot of background noise today, but I'm going to try to be speaking a little louder. As you can see, I brought the mic closer, and then I'm going to lower my overall volume, whatever. 1548, the most similar path in a graph. As you can see, I've already went through this problem. I have some notes ready and prepared for you guys. Anyways, so let's just read through the problem. We have n cities and m bidirectional roads, where roads of I is equal to A, B, basically one city to the next city, which connects city A with city B. Each city has a name consisting of exactly 3 uppercase English letters. So we'll see like ATL, DXB, HND, LAX. Given in the string array name. Starting at any city X, you can reach any city Y, where Y does not equal to X, meaning you can't go back to yourself. The cities and the roads are forming an undirected connected graph. Okay, so the entire graph is connected and is undirected. You will be given a string array target path. Okay, an array of strings called the target path. You should find a path in the graph of the same length and with the minimum edit distance to the target path. Great. You need to return the order of the nodes in the path with the minimum edit distance. So basically, we have this string, okay? This is our target path, okay? And this is the path. And what we need to do is we need to return the minimum edit distance of this path, okay, such that it can form a valid path within our graph, okay? And we're going to get our graph. We're going to see how the graph looks. What we saw how the graph looks is basically a two-dimensional array of basically called roads. Anyways, so we need to return the order of the nodes in the path with the minimum edit distance. The path should be of the same length of target path and should be valid. There should be a direct road between answer I and answer I plus 1. Yes, yes, yes. Basically 1 to the next, to the next, to the next. You can keep going directly. If there are multiple answers, return any one of them. The edit distance is defined as follows. I'm not going to explain the problem too much. I'm assuming, obviously, if you coming over here, you already read through the problem and you really got a gist of the problem. But before we get into it, there's one thing that's really important to notice, okay? And that's the core of the entire algorithm. Hey, Hafsa, can you go upstairs?
No play.
Can you play in the room? Okay, fine. Just keep your voice a little lower, okay? Alright, thank you. So, let's notice some things, okay? Basically, the solution is going to be some kind of graph traversal, right? Obviously, we have a graph, okay? It literally tells you it's going to be a graph, and it basically tells you need to go from one to the next to the next. So it's either BFS or a DFS. We're not looking for like distance between two nodes or anything like that. Or we're not trying to get from one node to the next node. It's not like we're trying to find a path from target beginning to the end. That's not what we're really doing. What we're really doing is we have this target path and we're just changing the entire path one by one. So usually when you're looking from one node in the graph to another node in the graph and you're trying to find some connection between them, you'll do some kind of BFS. But in this case, we don't need to do that, so we'll do a DFS, a depth first search, which is usually a lot simpler. Anyways, so let's notice some things, okay? And now I'm gonna try and explain this. Anyways, so we have our example 1, right? And we have these nodes. We have Atlanta, I'm assuming it's Atlanta, DXB, LAX, PEK, and HND. Hafsa, volume. Okay, a little lower. Thank you, Hafsa. I love you. Okay, so these are our roads, this is our graph, and these are the names of each of our cities, and then this is our target path. We're going from ATL to DXB to HND to LAX. One thing to keep in mind if you look through some of the examples is that these necessarily don't have to be names in the city. So this could be like VEE, right? It could be whatever it needs to be. Hafsa, lower. Don't scream, please. Thank you. I love you. Anyways, so we're going from 0 to 2 to 4 to 2, and that would be basically this is our graph. This is our target path, and we need to start changing cities in here so that it becomes a valid traversal within this graph. And so if you kind of look through it, you know, you'll see that the only one we really need to change is this one to LAX, right? We can just change this one to LAX, and that's a valid solution. So for example, we go from ATL to LAX, Instead of DXB, we'll go to LAX, and then we'll go to HND, and then we'll go back to LAX. And so that kind of works. And that's the traversal that's going on right here. So it's from ATL to one of them. Instead, we just change DXB to LAX, and then we keep going to HND, then to LAX. And that's valid within our graph, and that's basically one of the possible answers. And that had a minimum edit distance of just 1. Meaning, all we had to do was change only one of these items in the target path array to achieve our final answer. And that's all you need to know for that. Anyways, moving on from that, kind of took 5 minutes just to explain the solution, but let's notice some things, okay? So what we're going to be doing is we're going to slowly build up our solution array, okay? And it's kind of going to be like this. So we're going to find the distance between ATL, okay? Let's not explain it like that, okay? So we're going to start from the beginning of our names array, right? We're going to start at the beginning, okay? This is names, and this is the target path. And so we have 0, 1, 2, 3, and 4, okay? And what we're going to do now is we're going to slowly go through all the names, try to pick any start position, okay? And just search from there, okay? So we're going to start from ATL, and then we're going to check, is ATL different from the beginning of my target path? And if it is, then that means I have to change 1, right? I have to add 1 to my cost, and that means I have to make 1 edit. And therefore, I'll add 1 to my cost in this current depth first search, okay? Then I'll go to its neighbors. And so from ATL, I'll go to either LAX or I'll go to DXB. And so let's say I went to DXB, right? And if I went to DXB, then I ask again. I'm at DXB now. I populated my first index. Now on my second index. And so now I check. Is my DXB different from the second index at target path? And basically, it's not. Right, so 1 DXB will be equal to the DXB here. So once again, I don't need to add anything to my cost, so my cost is currently 0. Then from DXB, once again, I'll go again, and I'll check my neighbors. Okay, and now my second index, or you could say I'm third index, but index position 2, and I'll go again from DXB, and let's say I go back to ATL. I'll go back to ATL, and now I'll check. Is my item at index 2? Because that's what I'm at currently, that's what I'm trying to fill up. Is it different from what I'm currently at, which is ATL? And we'll say yes, it is different. And so for that reason, we'll have to make 1 edit. So I'll write ATL here, and I'll add 1 edit. So 1 edit was currently made in this depth first search. Then I'll go again from ATL, and I'll visit its neighbors, and I'll go to either LAX or DXB. Okay? And let's say I went to DXB back first. So I'll go to DXB. I'll check. I'm at index 3. Is that my item at target path at index 3 different from what I'm currently at? Yes, LAX is different from DXB, and therefore I'll have to make another edit. So I'll add in my DXB, and since I made another edit, I'll add 1 more. And so my number of edits was 2. And so now this is a path, and to get this path from my target path, I made 2 edits. Okay, I made 2 complete edits. But now let's say, so that returns, and then we go back. Okay, we start working kind of backwards. Now from here. So now I visit DXB. I got 2 as my final cost. Now let's go visit the next neighbor, the next child. So instead of going from ATL to DXB, I'll go from ATL to LAX. So from ATL, I'll go to LAX, and then I'll check once again. I'm at index 3. Is index 3 different from the index 3 at target item at index 3 in the target path? No. This is LAX, and what I'm currently at is LAX. And therefore, I don't need to add anything to my cost. And so now I have the same length. My current array, my current path is the same length of my target path. And to get there, I only had to make 1 edit. I only had to make 1 edit, which was HND. Okay? And that's kind of how it works. And so now I'll go through this, and it'll make a little more sense. So let's say I started ATL. Okay, I started ATL, I'm at index 0, and I ask myself, is it different from my item at index 0 in the target path? No, right? They're both ATL, this is ATL, and I'm currently at ATL. So I add to my cost plus 0. So my current cost is 0. Then I go into my child, right? One of my children. And we start at, let's just say, DXB. And so I'm currently at index 1, okay? And now I ask, is it different? Well, let's see. I go index 1 over here. No, it's not different. So once again, I add to my cost, just plus 0. Then from DXB, I go into my children. Let's go back to A first, right? I'm at index 2. Is it different? So at index 2 right now, look over here, my index 2 and target path is actually HND. HND is different from ATL. So yes, I have to make an edit. So I add to my cost plus 1. So now my current cost is 1. I'm summing these up. Then from ATL, once again, I have to go to another child. So let's just say I start with DXB. And now I'm currently at index 3, right? Because I keep filling it up. And now I ask myself, is it different? In this case, DXB is different from over here at index 3 in target path. Yes, it is. So once again, I have to add another 1 to my current cost, and I'll end up with 2, right? And since I'm at index 3, I reach the end of my the current length of my target path, and I don't need to keep adding. So I return 2, right? I won't return human answer, but basically now I know the edit distance from ATL to DXB to ATL to DXB is 2. Okay, from this to ATL DXB ATL DXB requires an edit distance of 2. So 2 edits were needed. Let's go back up again, and from ATL I go to a different child instead of DXB, and I'll go to LAX. And at LAX I start at index 3. I ask myself, is it different? And so I look 3. LAX 3 is different? No. So I just add 0 to my cost, to my previous cost, which was 1, and so I'll just return 1. Okay? I'll just return 1. Anyways, so now I go back up. ATL has no more children left, and then I go back up, DXB. And every time I find a cost which I'm returning, I'm saving it to some kind of DP table, okay? That I'm either memorizing it, saving it into a hash map, some kind of dynamic rolling double two-dimensional matrix, whatever, so on and so forth. So I'm finished visiting ATL. I go back up to DXB. Okay. So from DXB, if we went back a little forward, right? When we were at index 1, we went from DXB and we went to ATL. Instead of going to ATL now, let's go to PEK. And I go from to PEK, and I'm not going to go through the rest of it, but I'm going to finish this up so you kind of see what's going on here. So from PEK, I'm at index 2. And now I ask myself, is the item and target array at index 2 different from PEK right now? And yes, it is. So this is PEK, we're at PEK, but it's actually HND. So we have to make an edit to go from HND to PEK. So every time I make an edit, I add to my cost, and now my cost is 1. Because over here it was 1 plus my 2 previous costs, which were both 0. So currently I'm at 1. Did I reach the length, or did I reach my final index? No. My final index is at index 3 because the length is 4. So I just keep going. So from PEK, let's just go start searching. I'll go down to one of my children, which is DXB, or one of my neighbors, whatever you want to call them. Neighbors is probably better, a neighboring city. So I'm at DXB at index equals 3. But if you notice, we already solved DXB at index 3, and we had that cost. We kind of calculated that cost, right? And so therefore, I know the cost from DXB at index 3 was yes, and I know my cost was 1, right? At this point, not like previously. The way I'm showing you right now is not how we're going to be saving it when we're coding. We're actually going to be working like backwards from this approach, right? So we'll be saving what DXB, imagining you're starting at DXB at index 3 and you're working this way. So we'll be saving the cost from DXB at index 3 downwards. So actually when we return 2, it'll save 2 over here as the minimum. I don't know if that kind of makes sense. It'll make sense when you look at the code. Anyway, so we visited that. So we kind of already know what's going to happen. So we just return. At LAX, we also visit LAX at index 3. We kind of know what's going to happen, so we just return. We didn't visit HND at index equals 3, so we ask ourselves, is it different? Yes, we add to cost plus 1, and we return. Then we go back up back up, we go back up to ATL, then we go up to L, and then we go from ATL instead of to DXB, we'll go from ATL all to LAX. And once again, we just keep going like that, right? Index 1, is it different? Yes, so I add 1 to my cost, and then I go into it from LAX to ATL, and then the PEK and the HND. But then you'll notice I visited ATL at index 2 over here. I visited PEK at index 2 over here. I didn't visit HND at index 2. So I asked myself all the other questions and so on and so forth. So this is just one, right? This is only one where I started at ATL. Then again, I have to do this from starting at ATL and starting at DXB and starting at LAX and starting at PEK and starting at HND. And every time I do this, every time I go into it, or every time I start at a new starting point, right, I have to calculate the minimum distance. I have to keep track of which path returned the minimum distance, okay? And every time I do it, I'm keeping track of which one's the minimum, which one's the minimum, which one's the minimum, which one's the minimum, right? And eventually, once I'm done calculating everything, I'll just return my minimum and my minimum path, right? The one that ended up with the minimum cost. And that's the gist of it, and I'll walk you guys through the code in just a second. Alright guys, we're back, and this is the solution. After I did that little commenting, I kind of started writing out the code, and here it is. Okay, so this is basically how it works, okay? Like we talked about, the first thing we're going to do now is we're going to initialize some variables. We're going to initialize a visited this is basically a visited what am I looking for? A visited two-dimensional matrix. This is going to be basically our DP array or our memorization array, whatever else you want to call it. And so basically for each name, right? For each name, we want to see if we, at that current index, if it was visited. And that's basically this, right? So for this index, and the ATL will obviously correspond with an index. So for this one, at index 0, did we visit it or not, right? And that's what the visited, and if we visited it, what's the minimum edit distance that we calculated from there. So that's what visited is going to hold. The next choice for minimum is also going to do the same thing, right? So basically, let's say we're at DXB, right? And we calculated ATL and PEK, and they both return their edit distance, right? So ATL returned, let's say like, what does it return over here? In this case, the minimum would be 1. So ATL returned 1, PEK would also return 1, but let's say in this case it returns like 5, okay? So ATL returns 1, PEK returns 5, I don't know how that's possible, but whatever. And so obviously we'll choose ATL. So what next choice for min is going to save is the next choice to get the min, next choice for our minimum. So it's going to save DXB will go to ATL. So we know that at DXB, at index 1, the next best step will be towards ATL. And that's what that's going to save. So at this name, at this current index, what's our next best choice? And you kind of see that there. And then we save the target path, we save the name, and we kind of save the adjacent matrix. We fill our visited arrays with all negative ones. Because obviously an answer could be 0, and we don't want that, because what if 0 is actually the right answer? Anyways, and then we slowly just build up our adjacent matrix. This is pretty standard stuff. You can just read through that. And here's the fun part so now for each node, right? Remember how we said we started at each node, this one or this one and this one, this one, so we have to start all of them. So we're going to start at each of these nodes. We're going to go through each one of them, and we're going to start doing our depth first search from each one of them. And so now, basically, once we do the depth first search, we're going to get our edit distance, right? Our response is basically our edit distance. And depending on which one, and we're just going to, you guys know this, we're going to calculate the minimum edit distance. And basically, if our new edit distance is smaller than our previous minimum, we update our minimum. But what we also need to do is update our start value, right? So because we need to know which node we need to start at, which city, which name we need to start at. And so that's that. And so we'll walk through this DFS later, but let's say we got it, right? And so this DFS is also going to fill up the next choice for min. So as you can see, we're building the answer based on what's the next best choice. So we generate our answer list, and then while our answer size is less than the length of the target path, what we're going to do is I'm gonna add my start. So I'm gonna add ATL. I'm gonna add it, and then I'm gonna say from start at this index, which is 0, right? With size will now 1, we'll go back to 0. What's my next best choice? And the DFS will basically have filled this table out, right? And so it'll see my next best choice is either like LAX, right? Or it could have been DXB, it doesn't matter depending on the order we went into it. So let's just say it was LAX, right? And so then I say, okay, great. So then I set my new start to LAX, and I say, then I go again, then I add LAX in, then I keep doing that, then I keep doing that until eventually I just keep filling this up and I keep resetting start until my answer is filled up, and then I return my answer. That's the basic gist of it. Now let's just go into DFS, right? What's DFS doing? So we have our names index, which is basically this, right? ATL is at 0, DXB is at whatever it's at. In this case, it's at 1, right? HND is at 2, LAX is, sorry, this is a target path. ATL is at 0, DXB is at 3, PEK is at 1, LAX 2. That's our names index, right? And then we also need to know the index of our current path, or I just called it a target path, right? Because we're comparing. So it's either 0 or 1 or 2 or 3. It's going to go all the way up to the length of the target path, right? So remember, this one and this one, that's all we're checking, right? We're just seeing this and this index, right? And we're trying to see from this one at that index, is it different, is it not, and so on and so forth, right? For me, there's a time lapse. Like I took a 1-2 hour break. I did some other stuff, so I'm kind of thinking like, do you guys remember it? But obviously, if you're watching the video, you obviously remember you just watched it. Anyways, so now if we visit already, like we talked about, from here to here, then we'll return the previous count. How do we know we visited? Basically, if it's not -1, right? Because it was initialized to -1. Else, if it's different, we'll add 1. Our edit distance will go up. We'll increment our edit distance, or if it's not, we'll keep it at 0, right? If we need to change it, if what the current node we're at is different from the item at the current index we're at in target path. I don't know if that makes sense. I'm kind of not explaining this well, but I don't want to redo this. Anyways, so if PEK, and let's say we're index 3, and if that is not the same as in the target path our index 3, which is LAX, then we're going to have to make an edit, and obviously we add 1, or else we don't. But anyways, that's that. So that's what this is doing. If it's different, we add 1, else we add 0. Then we need to check. This is our base case. If we filled up our path, meaning if we've reached the final index, which is the target path at length -1, then we just return the edit distance. And now here's the fun part. So now let's say we didn't. So now we need to keep searching, right? We need to go deeper into our depth first search recursive calls. So what we're doing is from each neighbor, we're going to calculate the minimum cost. So basically for each neighbor, we're going to calculate the cost. And then from all those costs, we're keeping track of the minimum one, right? So for each of our neighbor, we're going to go do another depth first search inwards, right? And obviously we have to increment our current index. And then if our cost is less than the minimum, we set the minimum to the cost. And then also we have to fill this out, right? We have to say our next choice, our best next choice that will give us the minimum cost is obviously going to be the neighbor, right? Our neighbor. So I want to say that. So I want to say at my current index and my name's index to the current path index or whatever else you want to name it is basically at this one and this one, right? The next best choice will be DXB, or at DXB, which will be like, let's say at index, what is it index? Like 3, right? And 1. So that's going to be 3 and 1. Names index will be 3. Current path index will be 1. Our next best choice will be ATL or it'll be PEK, whatever which one it is. And that's what basically this line over here is what we're doing. And so once we're done with that, right, eventually we have a minimum. And what we do is we add the minimum to the edit distance. Or better yet, we add the minimum to the edit distance and we save it right into our DP array or our memorization array, whatever else you want to call it, visited array, and then we just return it. And that's the basic gist of the answer, right? And so that's how the DFS works. And so for each one, we're going to keep doing that, and eventually we'll have our minimum edit distance. And after that, it's very simple. Then we, like we explained before, we just build the answer based on what's the next best choice because the next best choice is already filled out. And so that's kind of how it works. Keep this in mind. Hope this helps. Video might have gone a little too long, but it's a hard problem, so I think that's expected. Hope you guys enjoyed. Hope you guys learned something. If there's any comments, likes, if I could explain a little better, just let me know. Yeah.